So my presentation today will be focusing on using 2D grillage models for the analysis of curved steel box girders for the purpose of load rating. Some of the highlights of my presentation will be how to use 2D grillage models as a refined analysis method when the AASHTO live load distribution factors can't be used, how the use of Midas MCT command shells can help automate the creation of large complicated bridge models, and then how you can use Excel workbooks with macros to streamline and simplify the data input. The combination of the Excel workbooks and the MCT command shell can allow for easy data input into an Excel table and then use a macro to create the MCT file to streamline the whole process. I'll also talk about ways to reduce the analysis runtime of these complex and large Midas civil models. The overall outline today will be a general project overview. It'll be a general brief load rating overview of the Fremont Bridge, which is what we'll be presenting about. And then we'll get into the Midas modeling, and then we'll have a short conclusion and then some time for questions. So the project that I'll be presenting on today was actually two separate projects for the Oregon Department of Transportation. The main project was to rate 26 steel box girder bridges, and this included a wide variety, including curved girders, large skews, flared girders, splitting decks, and also actually there was two railroad car bridges. These bridges were split into three groups. We were also tasked with developing the rating procedures for steel box girders and also developing tools for ODOT. And these will be included in the next load rating manual from Oregon. There was a very large project team, and the project managers were Lynn Hui, Joel Tubbs, and Matt Harlan. I also wanted to give special recognition to Eric Verluga, who had a very significant role and originally was the one who kind of came up with the idea of using the MCT files to help streamline the initial process. So a load rating overview, we'll do a kind of the general process briefly, and then some more kind of specifics about the ODOT procedures. Then we'll get into the steel box girder rating portion, and then live load distribution factors. So the general load rating procedure evaluates the bridge capacity to carry the current vehicles and accounts for the current bridge condition. Rather than doing a capacity over design, it subtracts your dead load from your capacity and then divides it by your live load effects. It's used to identify the need for load posting or strengthening, and then also is used in bridge management systems to prioritize repairs or replacements. The ODOT LRFR manual is their load rating manual, and it currently outlines procedures for 7 different structure types, pin and hanger, expansion joints, and cross beams. The current manual does not cover steel box girders, and that's what we were tasked to do. ODOT's primary software is brass, and for structure types that are not applicable to brass, they use Midas Civil to determine load effects, and then use Excel workbooks to calculate capacities and rating factors. For the ODOT load rating procedures, it includes 23 to 24 live load definitions, depending on the structure type, regarding span length and negative moment at interior supports. They have the standard legal trucks and specialized hauling vehicles, and then also have 3 continuous trip permit trucks and several single trip permit trucks. So the general steel box girder load rating process we used is first you obtain the bridge inspection report to determine the current condition and posting of the bridge. With that, you look at the current bridge plans, so you'll have your as constructed plans and any modifications. And then from there, you'll develop a scoping file to determine what members need to be rated. All three of those will go into the primary documentation of the MathCAD prelim file. This is where all inputs are documented that for calculations or assumptions. For the steel box girders, due to a complex geometry, this was also combined with AutoCAD or MicroStation files to help with geometry and node locations, and as well as Excel workbooks that were used to automate the production of the prelim file. From the workbooks, as mentioned before, they were also used to create MCT command shell files that were used to create the Midas models. And then the Midas models were ran to determine force effects for both dead load and live load. And from there, the output, or the force effects from Midas, were transferred into a tool we developed that's referred to the template, which calculates capacities and rating factors for the steel box girders. Those results are then copied into the primary ODOT load rating summary sheet, which is the stamped summary of the controlling rating factors. The steel box girder live load distributions are included in AASHTO LRFD. However, there's many restrictions for you to be able to use them. And for most steel box girder bridges, one of the advantages is their large torsional resistance, and so they normally are used for either skewed bridges or curved bridges, which both of those are constraints or restrictions that prevent the use of the AASHTO distribution factor. There's also several other restrictions, including spacing, overhang, and some other general ones. The 26 steel box girder bridges that we rated were split into 3 groups. Group A consisted of primarily straight parallel girders with minimal skew. These were decided to be approximately straight, and even though they might some restrictions weren't met, it was decided to use the AASHTO live load distribution factor applied to a single straight girder line model. When a spacing restriction was exceeded, the lever roll was used instead of the AASHTO distribution factor. Group B was for curved bridges that needed to capture the torsional effects. The model used was a single curved girder line model, which would capture the torsional effects due to the curvature. The live load application was applied by using a single lane load with a lever roll calculated distribution factor. The last group was of highly complex bridges with curved girders, flared girders, splitting girders, and skews greater than 10%. This is what the 2D grillage models were used as a refined analysis. And the live load was determined by using multiple lanes within the 2D grillage model. Now for the Fremont Bridge overview. So we'll have a brief description of the general bridge, and then we'll get into the east approach ramps, which are going to be the focus of this presentation and what the modeling will cover. The 2 bridges that we'll be focusing on today are 8958 and 8958B, which are both on the east side of the main span of Fremont Bridge. The Fremont Bridge crosses the Willamette River in downtown Portland, Oregon. It was built in 1973, and it's a very highly used structure. The main bridge is a double-deck steel-tied arch spanning over 1,000 feet. One unique thing about the Fremont Bridge is there's a lot of public outcry to produce a beautiful big bridge after the Markham Bridge, just south of the Fremont Bridge, was constructed as a low-cost alternative and was not very pretty to look at. The approach spans consist of primarily steel box girders and also some reinforced concrete box girders. There is a total of 15 different approach bridges. The east approach ramps connect I-5 and city streets to I-405, and the west approach ramps connect Highway 30 to I-405. DEA load rated all of the approach bridges and also inspected the east approach bridges this last year. So the two primary east approach ramps that we'll be focusing on today were both double-deck structures, had up to 6 girder lines per deck, included curved girders, flared girders, splitting girders, tapering web depths, and mini cross-section changes. There was also skewed supports, splitting decks, and in-span expansion joints. Now for the Midas modeling. So the topics of the Midas modeling will include 2D grillage models, model creation using the Midas MCT command shell files, model analysis, model verification, and model output. The 2D grillage models were used as the refined analysis method used to determine load effects for the bridges in Group C. These were the complex bridges and were primarily the double-deck Fremont ramps. They also included 3 heavily skewed bridges. A total of 9 unique 2D grillage models were created. The 2D model it was referred to as 2D because there's no depth associated to the model. So all the nodes or all the elements are modeled about their centroid on the constant XY plane. One exception to this was the rail elements were modeled at the bottom for graphical purposes and for checking. So the 2D grillage model that I'll be focusing on today will be for the lower ramp of 8958 and 8958B. These are the eastmost approach, or the 2 approach ramps directly east of the main Fremont span. The 2 both the 2 bridges were modeled together, as well as 2 spans of the 3 attached additional approach ramps. This was done to reduce the number of independent models that would have to be created and then tied together. The different bridges are connected with pin and hanger expansion joints, so the supporting span reactions would have to be transferred from one model to another, which is simple for dead load, but for live load it could get complicated. The model consisted of over 1,000 nodes, almost 2,000 elements, and over 13,000 different sections. There's multiple traffic line lanes applied for each girder, and the live load was applied to the cross beams. Almost all the model data was defined using MCT files. There was only a few things that were defined in the GUI environment, which included a few rigid links to model the splitting girders, as well as a few additional deck elements and rail elements at expansion joints and where the decks merge together. The 2D grillage model's main components consisted of the longitudinal composite steel box girder element, interior transverse composite deck element, a cantilever transverse deck-only element, so it's just the deck, and then a longitudinal bridge rail element, as seen in the photo before. One thing to note, as mentioned before, on this view, it looks like it's actually more of a 3D model, but it's just an extruded view of the 2D model. Midas has an option to align the top of beam section with the center line of the XY plane for display, which is handy for doing grillage models because it will place your deck on top of your steel section of your steel box girder. So using the MCT files to create the Midas model. I'll give a brief overview of the MCT command shell, the general procedure used, and then I'll get into several different areas that the MCT command shells were used for model generation, which included the initial model setup, creating nodes, creating the composite box girder sections and elements, boundary definitions, which included beam end releases to model the expansion joint and the supports. Also the transverse deck elements, the longitudinal bridge rail elements, dead loads, and live loads. So now I'll give an overview about the MCT command shell. It allows the use of text commands to create the model data instead of creating the data within the GUI environment. This allows to speed up model data creation for repetitive definitions. So instead of having to manually click and define each item individually, or even using the bridge wizard option, you can use a spreadsheet and macro to streamline the process and be able to do repetitive commands from either for a single bridge or for multiple bridges. It can also reduce errors in the model data because you're clicking less buttons and have less chance to accidentally select the wrong element or node when defining a model data. And it also can be used to automate the creation, Excel workbooks can be used to automate the creation of the MCT shell files, there's really a wide range of how complex you can make your workbooks and macros to do this. One thing nice is that you can make it very simple where it only does one thing, like creating your nodes, or you can keep building on it to make it do more and more as you feel needed. And the tools you develop can be used for multiple bridges and can be modified for different bridge types. Almost everything can be defined in Midas with the MCT files, and ODOT already has several MCT files available to use to define live load definitions, analysis options, and dynamic report data. When you insert a command within the MCT command shell window, it will populate the text command, and it will also provide a description of the command parameters. This can be very useful when you're trying to determine how the formatting and parameters when you're trying to create the MCT file or create a macro to produce it. One helpful thing is if you already have a structure defined or a part of a structure defined, you can go into the MCT command shell tool and select the command or data that you're trying to reproduce and click the insert data. This will then will show the parameter formatting with a brief description as well as the actual data. And then so you can create your macro to mimic that. The picture shown here is for creating sections. There's some good references out there for MCT files. There's the MCT file quick reference, which is listed here. This doesn't have every command, but it has the majority and most commonly used commands. This is very helpful because it kind of describes it in more common language than within the MCT file. So it helps kind of explain what each parameter is and what it's used for. There's also several other resources out there that you can obtain by Googling. So the general procedure that we used to create the Midas MCT files was first to create Excel workbooks to be able to easily document all the complex inputs, and then create a macro that would take that that documented input data from the spreadsheet and produce the MCT file. From there, you have the MCT file that you can run in Midas to produce the model. The general procedure for creating the total bridge model that I used was, first I would use a developed workbook to create the MCT file for each girder line of each bridge. There was a total of 10 girder lines that were rated for the 2 bridges, with additional 6 girder lines for the 3 additional approach spans, or 2 spans of the 3 additional approach bridges that were used to capture dead load and live load effects transferred through the expansion joint. The MCT file for the individual girder lines created the initial model setup, including nodes, supports, sections, elements, loads, and structure groups for each span. From there, a separate Excel workbook was used to create MCT files for the interior transverse deck elements. These were the elements that connected the multiple individual steel box girder lines. The MCT files created a modified concrete material property, composite and non-composite deck sections, interior deck elements, and structure groups. The next step was to use the same workbook to create the exterior transverse deck elements and longitudinal bridge rail elements. The MCT files for these elements created the additional deck nodes to model the edge of deck at each floor beam and pier location, the cantilever deck section, a stiffness scale factor, and the bridge rail element and structure groups. The final step was to use the same workbook used for step 2 and 3 to define the moving load parameters. The MCT file created the moving load code, vehicles, moving load cases, moving load subload cases, and traffic line lanes. The initial model setup from the MCT files included the project information, units, the structure type, material properties, which was only for the steel material property, static load cases, self-weight definition, load combinations, boundary groups, and custom dynamic report tables. As you can see, this one file created several different inputs or model definitions, and this one file can be modified slightly to be used for many different bridge types and can be used over and over again. The screenshots shown are some of the model data that those commands defined. Now I'll talk about using the MCT files to define the nodes. Defining nodes in the GUI environment for complicated curve geometry is not practical due to the fact that you have both the X and Y coordinate that's constantly changing along either a circular or spiral arc. The general options that you can use to create the nodes is either by directly typing in the coordinates or using offsets from an existing node within the GUI environment. You could also use the embedded node tables within Midas, and one feature or handy feature about that is you can directly copy nodal coordinates from Excel into the Midas table, which makes it quick. And the other option which we used is the MCT files, which will take it from Excel using a macro and create the MCT file with all the nodal coordinates. So the steps to define the nodes in Midas, first was to create the bridge alignment and framing plans in CAD. We use both AutoCAD and MicroStation. Then it would be to create the Excel workbook to combine and sort all of the analysis and additional geometry nodes needed for the load rating. Use the workbook to export the node station and offsets into CAD, and then export the node global coordinates from CAD back into the workbook and calculate nodal local axis. Then you would use the created macro in the workbook to create the node MCT file, and the final step would be open and run the node MCT file in Midas Civil. So now I'll kind of give a little bit more detail for each step. So the first step, creating the bridge alignments and framing plans in CAD. One thing to know is you only really need the alignment files created into CAD. With the complicated geometry of these bridges, it's very hard to try to determine the nodal coordinates without using a CAD software. One thing that complicates this is most of the times the alignment will be on a curve, and the offset distance to a girder is not to the center line of the girder, which are used for modeling, but to the exterior flange, and the top flange openings typically can vary along at any given span, which makes it very difficult to try to do it by hand, and can also make it more complicated to try to do it with Excel equations with a more black box approach. We chose to also draw up the framing plan for the Fremont double deck approach ramps due to the complicated geometry and kind of a lack of details in some of the original as-built plans. This wasn't something that would be required, but it was more just used as a general helpful tool. One thing that was very useful for it was when we first were creating the model to kind of have it, the actual structure shown in CAD, and then what our Midas model outline looked like before our tools were kind of fully developed and checked to kind of make sure everything was looking right. It was also very useful to determine girder spacing and some other deck geometry and girder geometry that would be hard to determine just from the plans alone due to tapering sections and splitting girders. The next step is to use the Excel workbook to combine and sort all the analysis and additional geometry nodes. So you'll see the bottom picture screenshot includes some of the special or the kind of key node points with the Midas station, which is measured along the center line of the element, and the bridge station and offset, which were then used to export into CAD to attain the nodal, the actual global coordinates. So that's what this step, so these points now were imported from, or exported from Excel and imported into MicroStation. From here, the points could be then exported out, or the coordinates of the points could be exported out and put back into Excel. From there, the nodal local axis angle of each node could be used. It was simpler to calculate the nodal local axis for every node rather than just at the supports, which is where you would need it. From there, using the created macros, the MCT file was created for the node and nodal local axes. The final step then was to open up the created MCT file within Midas and run it to produce the nodes. Next up, now I'll talk about creating the composite steel box girder sections and elements. This is one area that the Excel workbook proved to be very efficient. With very complex geometry and also just cross-section changes, it helped to be able to individually input each component of the cross-section separately and then use the Excel tool to combine them all and create your sections. As you can see on the top left photo, in this one region near a support, there's many different top flange changes as well as bottom flange plate changes. To expand on that, here are some screenshots from the Excel tool we used, which allowed for the individual component input. So the top left was calculated the general bridge length, but also allowed for the web thickness to be inputted. The top right was for your deck thickness and buildup. The next one down allowed for the top flange width and thickness to be entered in individually, and then similarly the bottom flange was able to do that as well. And then you had a overall geometry section where you could provide any kind of tapering width, or either deck widths or web heights in here. And this is also where the web spacing would be defined. And then from there you get you run your macros and you produce only unique Midas sections rather than having many duplicate sections. This was very useful to do, especially when some individual girder lines of a single bridge could have over 100 different unique sections. Boundary definitions were also created using MCT files. These included supports and expansion joints. The expansion joints were modeled with a beam end release command, which was used to release the moment at the expansion joint, which for this bridge were pin and hangers. And you can see in the screenshot of the spreadsheet that you can simply just type in ones or zeros for constrained or unconstrained for both the expansion joint or hinges and at the supports. So it makes it very quick and easy to define both of these. Next will be the transverse deck elements that were used to model the deck, floor beams, cross girders at the piers, and are connected between the adjacent steel box girders. There's three primary types of interior deck elements that were used. There were composite floor beams. So for these elements, at each floor beam location, the actual steel I-shaped floor beam was modeled using a composite section with a tributary deck, which was taken as half the spacing to the adjacent floor beam or expansion joint or pier. Similarly, we use composite cross girders with a tributary deck at the piers. These were typically rectangular closed box sections. At some locations where the deck would split, there would not be a floor beam, but the deck extended past. At this location, we would use a deck-only element that did not have any steel composite section. And the top right photo shows a kind of three of the kind of typical locations of these different types. The multiple transverse elements defined for the exterior deck elements, these are similar to the interior, but were only deck-only elements and were used to model the deck overhang. One thing to note is since the girder line models are just beamline elements and modeled about the centroid, the overhang distance of these exterior deck elements can be up, maybe 5 to 8 feet. And to avoid any weird model results from excessive deflections on a rather flexible section, a 50% increase in flexural stiffness was applied to these sections. And shown on the bottom figure shows the edge of deck node that would be created, the cantilever deck element, and then the bridge rail element that we'll discuss later that connected them. Now for the longitudinal bridge rail element. We decided to model the actual bridge rail element for several reasons. One is to capture the dead load effects for the actual location of this load, because depending on where your load is from the centroid of your girders, it can include or produce additional torsional effects. The other main reason was we utilized this exterior bridge rail element to be used as the reference element for defining the exterior lane load definitions. Shown in the photos in this slide shows how you can use the Midas section property calculator tool to go from what's shown on the plans, then draw in AutoCAD, and then import the AutoCAD drawing into the Midas section property calculator and create a Midas section, which can then be exported and then imported into the Midas civil section definition, which is shown on the far right. The dead loads used in the Grillage model were all created by the MCT files. These included applied loads, which included the primary expansion joint component self-weights, the top flange buildup, wearing surface wear applicable, and any additional bridge rail components such as a metal rail on top or a fence, and then also utilities. The self-weight was used to account for the self-weight of the steel composite box girder and deck, as well as the cross girders and bridge rail. A self-weight factor was used on the steel section and was set conservatively to 15% to account for stiffeners, splice plates, bolts, welds, and other miscellaneous steel components that were not modeled in the Midas section. This 15% was only applied to steel elements. To achieve this, a modified concrete density was used in order to avoid having that 15% be applied to the concrete elements as well, such as the deck. In Midas, it's not possible to only apply a self-weight definition just to a certain material type, so this was a workaround method. The deck self-weight was captured with the transverse deck elements, and so in order to avoid double counting the deck weight, the density ratio in the steel box girder section definition was set to 0. The one thing that was very useful from the MCT model, the MCT files, was to define live loads. For the live loads used in this grillage model, there was multiple lane loads or lane definitions for each girder that was to be rated. This could include up to 9 unique lanes for different configurations. And defining lanes for curved girders in Midas isn't too difficult, but it's easy to make a mistake, and it can be tedious when you have to do multiple lanes and then repeat that for multiple girders. The workbook macro would create MCT files to define the moving load code, the 21 vehicles, the single vehicle class for HL93, the multiple traffic line lanes with including the span start locations, as well as 20 moving load cases with sub-load cases. For the exterior girder live load, the lanes were positioned so that they were as close as possible to the barrier while meeting the 2 feet requirement. The the longitudinal bridge rail element was used as the reference beam element for the lane eccentricity inputs. The screenshot below shows the tab of the workbook that is used to define the live load, which only has a few simple inputs, including the type of girder, the number of lanes, and then you use your reference elements and eccentricities. For the interior girder, the lanes were positioned to essentially be centered about the girder, which became difficult with the splitting deck. For the splitting deck locations, individual lane load or traffic lane load had multiple reference or beam reference elements. Before the two independent decks merged together, the bridge rail element was used as the reference element, and then once they merged together, the girder centerline element was used. Shown on the bottom screenshot is a screenshot of the live load worksheet tool, and I created it to allow for 3 different segments to be inputted for a given traffic lane. And one thing nice about MCT files is that they're very flexible, so you can modify your tool to be more complicated if needed for different situations. Up to 9 unique lanes were defined for some interior girders, and this was to account for using either an even number of lanes or an odd number of lanes based on the placing for them. The moving load cases included the multiple presence factors, and for some interior girders also included sub-load cases for the odd and even number of lanes loaded. I'll now do a quick brief demonstration of how this tool was used. So this is one of the spreadsheets that was used to define the MCT command files. And essentially here you define what type of girder you're doing, the number of lanes loaded, and this was chosen by not placing a lane or a center of a lane past adjacent girder. You have the option to define lane names, and then down here you use your defined lane names and input your start and end elements for each of your reference elements with the eccentricity. Also, you can define the start span number to place that definition. There's 2 separate macros. One creates the lanes, and you can choose where you save it, and the other one creates the load cases. So within Midas, this model currently has no lanes or moving load cases defined. So we can go into the shell file, open up the file we just created, open and run, and now 9 lanes are just defined within a matter of seconds. And we can go see the lanes being defined. And you can see how they're going on either side of the individual decks and then coming together. Similarly, you can run your moving load cases, and now you defined 21 vehicles, 1 vehicle class, and 20 moving loads. And the moving load cases include sub-load cases for the even and odd lanes. So if you click on the sub-load case, you'll see this one is for 4 lanes loaded and allows up to, or minimum of 0 and up to 4 of the lanes defined. For the model analysis, with having these very large models, the analysis can take a very long time, up to multiple hours. When we first ran one of our models without even having live load, or maybe minimum live load for exterior girder, I think it took about 2 hours to run. Some of the options to reduce this runtime and make the analysis time more reasonable is first to run your analysis on your local hard drive rather than a project server. You can create copies of your base model for each girder being rated, and for those models can have separate live load definitions rather than having too many lanes for one model to be ran at a time. I believe it's a default, but there's a GPU acceleration option that essentially allows your Midas to use more memory of your computer and slow down other applications, but make the analysis run faster. Another option that was very useful was in the moving load analysis control data, is going from instead of the exact method to the quick method. This sped up the analysis runtime significantly, but it did not result in a significant decrease in the results. Several files were checked using both the exact and quick method as a comparison, and the percent difference was minimal. Another very useful option is to use the calculation filters within the moving load analysis control data to allow for to only run the live load analysis for the desired output that you're looking. Shown on the screenshot, a structure group called output was created, which only included the girders of interest that were going to be rated for the particular live load setup for that model. For model verification, the use of structure groups can help to individually view single girder lines and single spans to either check deflection or max moment locations. The dead load deflections can be used to check against the as-built camber diagrams to get a rough idea that your model overall is behaving appropriately. For model output, nothing too special here, but it's pretty handy and easy to take the output, the results tables into an Excel worksheet. And for this case, the output was taken into the tool we developed for ODOT, which is referred to as the template, which calculates the capacity and rating factors for the steel box girders. So the conclusions of this presentation are: 1, the 2D grillage models are effective refined analysis option for complex bridges with live load, for when live load distribution factors are not applicable. Using MCT command shell files to create large and or complex models can save time and reduce errors. And Excel workbooks or spreadsheets with macros can be used to create the MCT files to streamline the whole process. And that concludes my presentation today, and now I can answer some of the questions you guys have asked. So one question was the barrier rail included just for the stiffness model, or was it also included in the structural capacity used in the rating calculations? And what was the justification? So the barrier rail element, its primary purpose, one, was to connect the cantilever deck elements together. The other purpose was so you had a reference beam element for defining the exterior girder lanes. That way you could easily just have a constant offset from that element for your lane placement. It wasn't included for it wasn't really needed for necessarily the overall stiffness of the model. The stiffness of the barrier element compared to the steel box girder section is pretty minimal. And the other part was it used for the structural capacity? I don't believe we took advantage of increasing the effective flange width of the exterior girder for having a composite concrete bridge rail. But if that was done, it would have been done in the post-processing spreadsheet and wasn't used within the model. So one question was, what was the reason for using both AutoCAD and MicroStation for creating initial model geometry and nodal coordinates? And why not just use one CAD program instead of both? Both weren't used at the same time. It was essentially they were used interchangeable. So we had some people that were working on the project that preferred using AutoCAD or didn't know how to use MicroStation or vice versa. And so our workbooks were created to help use or to allow the use of either one. For using the nodal coordinates, they both can do the same task. The only one I believe AutoCAD is required for potentially is for creating the Midas sections. Another question was, were you able to assign structure groups using the MCT file? And that answer is yes. It's actually one of the more handy options. So you can see in my Midas GUI environment, this was the model already created, but the MCT files created over 100 structure groups, and what they do is, open up one up real quick. And so it's very simple. It's just a single group command, and then all you need to do is provide your name, so the superstructure group element name, and then you just define which elements are included in that group. And so when you create your macros to define the elements, assuming that you're going kind of in order for the elements, it's easy to kind of if you're defining your peer locations also to define to include a group definition because you already know the start and ending element. One question was, were the Excel spreadsheets with the macros, if they were created by me or if they can be found on the ODOT website? The only spreadsheet that will be available on the ODOT FTP site eventually will be the final template file that you import the Midas output into and calculate which calculates your capacity and rating factors. That spreadsheet does include a sheet that produces that you can input the individual Midas section parameters, and you can use that sheet to create an MCT file to create your Midas sections. But the other ones were created as kind of an internal working tool for part of this project. The main one that creates more of the steel box girder line elements, that was developed primarily by Eric Verluga, one of my coworkers, and I developed the deck elements and live load